What's up, everybody? My name is Eric. Welcome to my channel, Eric the Tutor. What's up, everybody? My name is Eric. Welcome to my channel, Eric the Tutor. Today, we're going to be continuing our discussion on SN2, SN1, E2, and E1 reactions. All right, so let's go ahead and jump into it. Last time, we talked about SN2 and SN1. Today, we're going to talk about them again, except now we're going to consider the solvent and what kind of effects the solvent may have on the reaction. So let's start with an example. Let's say I had something like Br with, let's say, SH minus, and I wanted to react it in DMSO, okay? So again, what did we say were some of the requirements? What are some of the things we're looking for? We are looking at our substrate and we're determining if it's primary, secondary, tertiary. So in this case, is it primary, secondary, tertiary? Yeah, it's going to be secondary. So here we have secondary. Awesome. Now we have a good nucleophile here. This is a good nucleophile. We have 3 lone pairs and we have a negative charge. So this is going to be an excellent nucleophile. Now, what is DMSO? Why did we choose it? Well, I could have chosen something that was like, I'll go ahead and draw. So if we have something that looks like this, or maybe we had diethyl ether, these are different examples of something we like to call polar aprotic. Polar aprotic. Now this is going to be important. We're going to contrast this with an example down here where we use something called a polar protic solvent. All right. Now what this means is if I wanted to react my nucleophile with my substrate, then I needed to take both of them and put them into a beaker. Now this beaker needs to have some sort of medium. There needs to be some sort of liquid floating around. If, let's say, I had water in here, and I decided to dump in some SH and dump in my substrate, okay, then what's going to happen is all of this SH, or at least a lot of it, is going to be interacting with this H2O. It's going to do hydrogen bonding with the sulfur and the hydrogens and the oxygen and the hydrogen. So if here's another SH floating around, maybe the O is interacting with the hydrogen. So instead of our SH being a good nucleophile and doing its job at kicking out this leaving group, it's instead interacting with our medium, and it's going to give us poor yield. Okay, this is going to give us poor yield. So we're not going to get what we want. But if we use something like DMSO, let's say we use, here's our beaker, and instead we have some C-double bond O floating around, so we have some DMSO, or let's say we have some diethyl ether. These, although there's an oxygen on each of them, they're unable to do hydrogen bonding because, let's see here, if we had our SH minus, there's no available hydrogens to be able to do any type of hydrogen bonding. Even this carbonyl oxygen here is not going to be interacting significantly with the hydrogen there. So when we put both of these in, let's say this beaker, then our SH and our substrate can have better yield and we can get our final product. So let's go ahead and draw what we would get. So if we had this group, we know our SH is going to do SN2. It's going to kick this out directly, and we're going to get something that looks like SH, okay? So it did SN2. Let's go ahead and divide the page, and let's give a different example. So let's instead say that we had something that looked like, here's a methyl group, and we had a good leaving group here. And instead we reacted with, let's go ahead and keep the SH. Okay. And this time I'm saying we're going to react this in H2O. Okay. So that means in our beaker, we have water floating around, okay? And we have that same nucleophile, So didn't we just say if we use this nucleophile that can undergo hydrogen bonding, that we would get poor yield? Well, under SN2 conditions, we would have gotten poor yield because the goal of the nucleophile is to be able to attack at that carbon and do it in one step. But what's our goal for SN1? So this is SN1. The first step is for the Br to leave, and then we have something that looks like this with a carbocation. For SN1 to occur, we want to have tertiary. We want to have a poor nucleophile. In this case, we have a decent nucleophile, so we can still do SN1, but we have to be in a polar protic solvent. So if we were in, for example, a polar aprotic solvent, then this nucleophile would be too reactive. It would want to do SN2 style conditions, but we know SN2 does not like to occur if we have tertiary. So these are two exceptions to we have to be careful of. Okay, so this we have secondary and we have a good nucleophile. This needs to be in a polar aprotic solvent. If this were instead a polar, if up here we were in a polar protic solvent, then that water would interact, or it could have been anything that's capable of hydrogen bonding. It would have interacted with our nucleophile, and we wouldn't be able to do SN2 attack as well. Here, we don't want SN2 attack to occur that well. We want it to be more SN1 style, so instead, we put that polar protic solvent so that the solvent interacts with the nucleophile. That way, this can just join on later as such to give us a final product that looks like just like that. Okay? Hope that helps, guys. See you next time.